So let me pull up a whiteboard. Actually, how about give me a thumbs up just so I can tell that you're alive out there. Okay. So you should all see the whiteboard. Where am I? Okay. Where were we? So we've been working with not green caps. Sorry, one sec. Can you hear me? So I can't see the chat. Would somebody just say if you can hear me or not?
Yeah.
Yeah.
Okay, thank you. We've been working with caps. The lab this week is involving a capacitor. We're going to look at the effect of adding a dielectric. There was a small video that was posted on the effect of a dielectric and kind of how to visualize how that changes the situation. But sort of where we were coming from is, we read what? Okay. We talked about combinations of capacitors. We looked at them in series and parallel. We derived, the rules for adding them. I suspect that's kind of familiar from your circuits background. We talked about, the fundamental thing with a cap being that it's a device that stores charge and energy. And we looked at the energy that's, or we stated the expression for the energy stored in a capacitor that looks like, depending on what flavor of this expression, you can have a version that has constant charge or a version for constant voltage, etc. And we looked at the rules, like caps that are in parallel just add. And when they're in series, you add one over, just like you would do for resistors. So kind of that's where we were coming from. And then the main thing was the capacitance for a parallel plate configuration. So looks like depends on the geometry. So the area of the plate as well as the separation between the plates, and it also depends on permittivity of free space. Now this would be for the situation where you have just air. And what we're going to do in lab is we're going to see what happens when you add a dielectric. So a dielectric is just another word for an insulator, i.e. not a conductor, something where the charge is not able to move all around it. And what happens in this situation is that the capacitance is modified. You get a factor, K. And this is the dielectric constant. And this is just a number. It doesn't have any units. You're just multiplying the sort of initial capacitance by some number. And this has two consequences associated with it. One is that this, can boost the capacitance. So it's a way to get a larger capacitance, which is good if you want to store more charge or energy. The other consequence to this practical consequence is just that it's difficult. So notice, you could make your plates closer together, and that would be a way to increase the capacitance. But it's really difficult to keep a geometry where you have things that are really close together but aren't touching. And it ends up being like a pretty fragile situation. So just practically, you can have a dielectric that's in between the plates that has gives it some mechanical strength. So you can imagine like a layer of insulating material, so where it's all rolled up. So maybe I'll say this is just, this also, it gives it some structure. So kind of practically speaking, a lot of times you don't have like a big sheet like this, although this is what it will look like in lab. Instead, what you do is you have like a layer of metal foil, and then, I don't know, here in a different color, and a layer of an insulator, a dielectric. And instead of it being, like a big sheet like this, you take that and you roll it up. You can make a package that takes up a lot less volume and is more robust, and it's just easier to work with. So imagine like I don't know, a roll where those things are kind of rolled up together. This is not the only way that these are made. They're made a lot of different ways, but this is a good way to visualize it. And we could ask questions, since we've incorporated this dielectric constant. Whoa, hello. Sorry. As an example, just of the kinds of things that you might be expected to do with this. As an example, let's find the dielectric constant for a configuration where we have a cap with an area A of 1 meter, a plate separation, so of like 10 microns, and we measure its capacitance, say, in that it is 10 microfarads. And so the question is, what K gives us that? So you could see we could just do a little algebra here. Our expression, if we solve this for the dielectric constant, we're going to have d over A times the capacitance divided by epsilon naught. And we can put in our numbers here. So this is 10 microns, i.e. 10 to the minus 6 meters, times 10 microfarads, so that'd be 10 to the minus 6 farads of capacitance. The area was 1 meter squared, and then epsilon naught, which is 8.85, 10 to the minus 12. And if we crunch these numbers, you can see it's going to, we have 10 to the minus 6, 10 to the minus 6, 10 to the minus 12. It's going to be a smallish number. And if you crunch these numbers, we would find that this is about 11.3. So, and that doesn't have any units because it's just the dielectric, multiplier, and which is a reasonable value. The value of the cap that we're going to look at in lab is different than that, but this can vary a lot depending on the material and the construction. Questions so far? Pretty straightforward.
I had a question. I was just wondering what K's units are. I don't know if you said that. I missed it or what.
K is unitless.
No units. All those cancel out. Voodoo magic.
Yeah.
All right. All right.
Yeah, we could. Well, let me see here. Yeah. You may see this in your text as well as sometimes you see epsilon specified as like just epsilon, not epsilon naught. And then this would mean that this is K times epsilon naught. So in order for this to have the same units, this K is unitless. Other questions?
If you have something in that area that has like good units you want to convert to meters or something, what do you have to do? Again, you have to like multiply the.
Yeah, that's a good question. This is something that commonly crops up. And we may have seen this with the electron deflection lab, where we were working with something that had units of nanoseconds squared. If you have, so suppose you had something that was in an area of like 1 centimeter squared, and you wanted to get it into meters squared. You would have to multiply this by a conversion factor, but you would then have to square the conversion factor. So in other words, you know that this is, that there's, 100 centimeters per meter. But in order to get this to work out, you would have to multiply, you'd have to square that factor. So 1 divided by 100 squared, you would have 1,000th of a meter. And you can kind of square meter, and you can kind of visualize that with units like this, where, if you imagine like a thing 100 by 100, you know that that's going to be less than 1/100th. It's 1,000th. Does that clarify that?
Yeah, thank you.
Mm-hmm. Other questions? So this is directly applicable to the lab this week, which I like this lab because it connects really well with the stuff that we're working on. So it's directly about capacitance and the addition of a dielectric, but it's also a really good practice for working with propagation of uncertainties. So there's a video example that's posted. I don't know what's going on. I'm having problems with the video recording. So like the last few minutes of it, the sound is messed up or something, but you can follow along. I mean, you can still hear me, but I'm like low or something, or I don't know. But so relevant to lab, let me kind of motivate and pitch the lab a little bit, and then we can see if you guys have any questions about that. So what we're going to do is, you could imagine we're basically going to vary the amount of the plates that are occupied by a dielectric, and then that's going to change the capacitance of a capacitor. We're going to measure this thing with a meter and then see, how its capacitance has changed. So you could imagine doing this in different ways. Like you might have like a dielectric sheet that you slide in, and then depending on like how much of it is in there, it's going to change, the area that would have a dielectric. What we're going to do is we're going to have washers made of plastic that we're going to put between the plates, and we're going to change the number of washers. So, and you can see how, the more that you add, the more of the area. So just if you look at this from the top, the more of the area of this that's going to be occupied by the dielectric. So if there weren't any washers and this thing had some area, A, that capacitance would just look like epsilon naught A over D, where D is this, this separation between the plates. So, and as you add those, what's going to happen is, this capacitance is going to become, we're going to lose some amount of area that's occupied by just air. So N here is the number of washers. So as you lose, as you add washers, you're going to lose area that's occupied by air, and you're going to gain capacitance associated with the area that's occupied by those washers. So you would add to this N Now these contributions will have the factor of K because they have the plastic in there. So it'll look like that. Now we can reorganize this. So if we take the K and then you notice this is all the same stuff except for the factor of K. So this looks like K minus 1 times that stuff. And then we have left over this A over D. And so what we're going to do is we're going to make a plot of the number of washers and then the capacitance as you add washers. And you can see that this looks like a line where, so the number of washers is N. So actually, let me just switch this around here. So this would give you the slope, and this is the intercept. And so you get a line, and the slope of that line, you can extract from it. You can get K. And the intercept, you can get epsilon naught. Now, that's the the capacitance part, and it works pretty well. And it's kind of cool that we're going to be able to measure a fundamental, this fundamental constant as well. So K just depends on the material. It's not like that is a special, we don't know the value. There's not like a known, it's not a constant. It's just a material property. This epsilon naught though is that's a fundamental constant, and we're going to be able to measure it with this kind of humble lab, which is kind of neat. And the other kind of useful part of this is notice like the propagation of uncertainty situation is going to be a little more complicated with this than what the labs that we've done so far. So the additional video that's posted will help you with that. We can talk some about that during the session to kind of get you pointed in the right direction, but there's also other resources that are posted. This is just because of time constraints. So we're talking about this now because you're going to need your time to take your data, and we just don't have enough time to both motivate it and take the data and do all the analysis during the lab time. So let me just put a note here. Refer to posted video for extra help with that. The propagation of uncertainties. Okay. Do you guys have any questions about this lab or kind of what I've proposed for you? Questions about caps and whatnot?
So for the I walked through the thing that was posted below it, and do you have to take 10 measurements of both the areas and then just take the average of that for the?
I don't think we're going to do that because it's kind of tedious. So I think what we'll do for deriving those measurements is we'll just pool the measurements of folks in the class and then do our statistics on that pool to get an idea of what the uncertainty is.
All right.
Yeah, just to save some time. And also to get us to, interact and work together a little bit. But that's a good question. Other questions? So you're all ready to go with this lab? That's cool. Okay, so we'll go ahead and talk about the next thing that we're going to get into then. Why don't you give me a thumbs up? Just tell me, just to tell me that you're there. Or something in the chat. Okay, cool. So where we're headed next is basically circuits, and we're going to talk about in the rest of our time today, kind of some of the fundamentals that we need to understand for circuits. But this is going to be chapter 25 and 26, and I'll get this stuff posted soon, as soon as I can figure out what's going on with my video recording stuff. So I'll post clips for that cover much of the many of the sections for 25 and 26. You're not going to be responsible for all of it, and we're not going to like rush through all of it during this session since we're still like right in the middle of capacitors. But basically, we'll look at sections 25, most of chapter 25. Most all of this I think will be familiar, and this is what we're going to talk about today. And then in 26, we're going to do basically about a chunk of it, but not all of it. And that's because one main topic that I think that you guys already have, or many of you had already worked on with, that you're not going to be responsible for in this course is Kirchhoff's laws. So we're not going to have you're not going to be asked to do basically, you're not going to be asked to do circuits problems that require you to use Kirchhoff's laws. Okay. So with regards to chapter 25, I think you will find this is pretty familiar territory. So this starts with, up until this point, we've been talking about electrostatics, right? We've been talking about charge. And basically in chapter 25, what we do is we go to current. And I suspect and hope that you know that current is related to charge because current is a charge that's changing in time. So in other words, the current you can think of as the derivative of charge. And this is, you talk about one of your main, ingredients for looking at circuits. You need to know how currents are going to move. And the kind of the basic law that we made use of in the first lab but haven't talked about is Ohm's law. So they introduce it for you in chapter 25. You can think of this as telling you how current depends on voltage. So current is proportional to voltage through the resistance. So if you have a large resistance, you're going to have a small current. If you have a low resistance, you'll have a large current for a given applied voltage. And sometimes you see this plotted IV curves. You'll probably see these if you're like EEs and stuff as you go forward. But you can see, this is a linear relationship. And if the current is really low, you would have, steep. But if the if the resistance is really low, you would have a lot of current for as a function of voltage. But if the resistance was really large, you would have less. Okay. And you can imagine doing all kinds of, different kinds of problems and stuff with that. But we're not going to really dwell on that at the moment because I think it's probably pretty familiar. The ingredient that we're going to add that is a little more physics oriented is this. How do you determine this resistance? So the resistance depends, one simple model of resistance is that it depends on the geometry and it also depends on the material. So it looks like this. Okay, where this is something called the resistivity. This is the area, and this is the length. The area and length of what? Well, imagine like a wire or a cylinder of some material that has, some area, it has some length, and it's made out of material that has a certain resistivity. And as you would imagine, conductors have low resistivity. So, and the lower it is, the lower the resistance is going to be for a given, geometry. Let's see, and so just sort of qualitatively, you can imagine if you had, comparatively long and skinny versus short and fat configurations, this would be a lower resistance because the area is large and the length is short, and this would be higher. So question for you guys, have you seen this idea of resistivity before? Where did you guys, I would expect you hadn't, but maybe if you have, where have you seen it? Just out of curiosity. It's totally fine if you haven't. We're gonna, we'll get this built up. Circuits, you talked about it in circuits. So let's look at a couple simple things that we can do with this. Yeah, like I said, I don't expect you to have seen this, so it's fine if you haven't. So you can do things like find the resistance of a configuration. Oh, and I should say this resistivity has units of ohms times meters because you want ohms times meters. So you're multiplying this thing by a factor of 1 over m, 1 over meters, because you have meters over meters squared. So this would give you, units of meters when you go to calculate a resistance. But for example, let's find the resistance of a 1 millimeter copper wire. So 1 millimeter diameter, sorry. 1 meter in length. So, and copper has a resistivity of, let's see here, 1.68 times 10 to the minus 8 ohms times meters, according to your text. So pretty simple. We just multiply this stuff together. Being mindful, we have to, get our units to work out. So the length is easy enough. That would be in meters, but the area would be pi times the radius squared. And when you crunch these numbers, you would find that this is 0.02 ohms for this configuration and material. So kind of a related question that how about I will have you work on and for a minute. So for this length, how small diameter would our wire need to be? For the resistance to be 10 ohms. So can you guys solve for the diameter? How about I give you a couple minutes to work on that? Is it clear what I'm asking you to do?
Yeah.
So give that a shot. And when you get a number, you can throw it in the chat and we can try and converge on a result. Yeah, same resistivity. Sorry, copper. Let me indicate that. That sounds reasonable. 46 microns. Other folks getting the same thing? Calculating the same thing, not just agreeing. It occurs to me I'm looking at my solution and I left out a factor of pi, so my number is not right. So, but it's close to that. So we would need to solve this for d. So maybe we would look at it like rho times length over pi times r. Take a square root. We'll pick up a factor of 2. So whatever evaluating that gives you. Other folks are getting the same thing? Is that what the thumbs up on that means?
Yeah.
Excellent. Okay. So, that's just an example of the kinds of questions that you might be expected to be able to do with that. It's sort of like somebody mentioned, kind of like working with capacitors and stuff in terms of just like doing some algebra and determining values. Okay. There's one other thing that we can build onto this. This resistivity depends on the temperature. And actually, this is really useful. So in one way, it sort of adds a complication because it depends on what temperature that you're operating at. But in another way, you can think of this as you can use the resistance, the resistivity and associated resistance with some piece of wire or something as a temperature sensor. So you can see from this, it looks it's going to increase as you increase the temperature. And so you can use it as a sensor. So as a really simple example, So generally, what this means is you have to know the material property. So in addition to the resistivity, you need to know this alpha, the resistive, how it depends on temperature. And as a really simple example, think about a light bulb. So we know that the resistance is proportional to the resistivity. So if we assume, and depending on the scenario, this is a good or a bad assumption, but if we assume that the resistance is more or less constant, or the geometry is more or less constant, then this becomes the resistance as a function of temperature, looks like the resistance at some base temperature plus this. And so just in our last minutes here, for a tungsten filament, light bulb filament, the temperature of that can get really hot. So this is an example that's mentioned in your textbook, like 3000 K. And if this tungsten has this alpha is 0.0045. So if we put those numbers in, we can solve for the relative resistance as a function of temperature, where this is like 3000. The temperature, room temperature, a good estimate of that is about 300 Kelvin. You put those numbers in and we would find that this would be a factor of 13. So if you change the temperature a lot, this can have a big impact on the resistance. So moral of the story, resistivity depend on temperature. So this is just for a light bulb filament. And we're already a minute over. Does anybody have any questions? I would mention qualitatively, this is bad, right? If you're talking about circuits. So resistors are not usually made out of materials that would have this, that would be this temperature dependent. Their resistance, so they'll make them out of carbon, and that has something like 10 times less temperature dependent resistivity. Questions? Well, feel free to reach out if you have any other questions. Otherwise, have a good day, and I'll see you, some of you in lab. Thank you for your attention.
Have a good day.
Have a good day.
Hey, Dr. Simmons.
Yeah, what's up?